Okay, so this is work with Christian and Jeff Kahn, who's not here for some reason, who I hoped would be here, but he's not, and Lotzi. Okay. So, and this is the first of two talks on sparse graph convergence. So this is some work that we actually did a couple of years ago, but was recently published in RSA. Okay, so now I have to turn this on. I think that'll work. Okay.
Well, couple means European couple, 10 years.
Yeah, right. Well, no. The sparse graph thing, how long? 5 years? 7 years? Okay, 7 years. Yeah, well, Lotzi had a few extra responsibilities, and we had a few extra responsibilities, and Lotzi was more responsible than we were, but that's still not saying very much. So, okay, so some motivation. Then I'll quickly go over some things that you heard from Lotzi on Monday and from Vera this morning on graph convergence for dense graphs. I'll just talk about the two main kinds, the left convergence and the right convergence. There were some others that you heard about. Then I'll talk about graph convergence for bounded degree graphs, which is much harder than for dense graphs in a lot of ways. And if you come from stat mech, then you really understand that, because a dense graph is a mean field graph. It's how everything behaves in the average field of something else. And on sparse graphs, it's much harder. But we are able to come up with something there. And then I will do something that I haven't seen many people doing in this workshop, which is I'll try to give you a proof. We'll see if I succeed in giving a proof. Okay, so why are we interested in this? Well, this started now, about 7 or 8 years ago. We were thinking of growing graph sequences that people were concerned about, and we wanted a succinct but faithful representation of those sequences, of the limits of those sequences, so that we could do sampling, testing. And so, the first thing that we asked 7 or 8 years ago was, given a sequence of graphs, what is the correct notion of convergence of those graphs, or what's a natural notion of convergence? And so you heard this morning about some of the work that we did on dense graphs, and it turns out that there are many natural notions of convergence. There's what was called left convergence and right convergence, which I'll go over. There was convergence in the cut metric. There was what Christian will talk about a little, which is quotient convergence, when you mod out by the partitions of the graph, relations to testing, to SEM-ready partitions. But this talk is going to be about left and right convergence for sparse graphs, for bounded degree graphs. Okay, so just to get the notation straight, if we have two simple graphs, f and g, then something is called a homomorphism. If it maps the edges of g, which I want to think of for the moment as a big graph, into the edges of f, which I want to think of as a small graph. So, other way around, sorry about that. Okay. So for left convergence, but this I do mean, I want to think of f as small, and I want to think of g as large, okay? And I want to think of probing my large graph with my small graph, just looking for copies of my small graph in the large one. So this is a very local notion. And so for this, it's natural to define the subgraph density, which is the number of homomorphisms properly normalized by 1 over the size of the large graph to the size of the small graph. It's also the probability that a random map is a homomorphism from the small graph into the large graph. And we say that a dense sequence of simple graphs, Gn, is left convergent if these subgraph densities converge for all simple graphs F. Okay, so, we test the edge density, the triangle density, the Peterson graph density. If all of these converge, then we're fine. A really simple example is the random graph, where these are just P, the edge density, to the number of P, the edge density of G, to the number of edges in the small testing graph F. Okay, so that's left convergence. Right convergence is a little less obvious to a combinatorialist, maybe, except if you're Dominic Welsh or something. But it's a very natural thing from the viewpoint of a person coming from stat mech. So for right convergence, what I want to do is I want to consider homomorphisms from G into H. I want to think of H as small and G as large. So what I'm doing is I'm counting the colorings of the big graph G with the little graph H. So if I were doing the independent set problem, I would just have a small graph H with 2 vertices on it. And okay, so then I can think of home as a partition function, okay? And so if I have a partition function, then what do I want to do with it? I want to get an energy out of it. So, this is important. For dense graphs, I don't want to exclude any color being next to any other color. So I may want to penalize it, but I don't want to exclude it. So all of the edge densities I want in H, I want to be positive, okay, strictly positive. So H is called a soft core graph. So I don't want to think of the independent set problem for my dense graph here. Okay. So now what I want to do, since this grows exponentially in the number of vertices squared, because I'm dealing with a dense graph, I want to take the log of this thing, okay? But it turns out that rather than looking just at homomorphisms in which I don't tie down the number of vertices of a particular color, I'm going to want to do a little more than that in the dense case. I'm going to want to say I want a percentage A1 of color of vertices of color 1. I want a percentage A2 of vertices of color 2, and so on. Okay, up to my V of H colors. And so this is what a physicist would call a microcanonical partition function. Okay, so I'm restricting. This is like saying in an easing magnet, I want so many upspins and so many downspins, or such and such a percentage of upspins and downspins. So I'm going to look at this quantity here, which is the number of homomorphisms, or the partition function where I have restricted it in this way. And then I can do a microcanonical free energy. So this grows exponentially. And so what I'm going to do is I'm going to take the log of it, and I'm going to divide, since this is a dense graph, by V of G squared. And this is a microcanonical free energy. And I'm going to say that a dense sequence is called right convergent if this converges for all soft core H, for all H with strictly positive edge weights, okay? And for all unit vectors A, so for all percentages of color 1, color 2, up through color V of H, okay? And it turns out that if we have a sequence of dense graphs, then this sequence is right convergent if and only if it's left convergent, which is at first, I think, not at all obvious, because left convergence, we're dealing with a very local notion. We're dealing with knowing all the subgraph frequencies. And right convergence, we're dealing with an a priori pretty global notion. We're dealing with the energies for all models H, which allow different colors to be next to each other. Okay? So that's what we did for the dense graphs. Vera talked about that a lot this morning. What do we do for sparse graphs, for bounded degree graphs to start with, okay? So what I'm going to assume is that all of the sites in GN have at most D neighbors, okay? So bounded degree, uniformly bounded degree in N. And in very much the same way as we did in the sparse, in the dense case, we're going to say that, okay, here the right normalization for the subgraph density is to divide through by the number of sites in the big graph G, okay, so V of G. So I'm going to take the subgraph density, and if that converges for all simple connected graphs after, edges, triangles, four cycles, Peterson graphs, and so on, then I'm going to say that it's left convergent. So that's a very similar notion. That's pretty much the same notion that we just had in the dense case. Right convergence, so here I'm going to say that GN is right convergent on H, so I'm specifying an H, if this free energy, so I take the log of this, but I just divide by V of G, not by V of G squared, because this is growing exponentially in the number of sites, because it's a sparse graph. Okay, if this converges. So what are the differences to what we did in the dense case? Okay, well, in the dense case, we had to use microcanonical free energies. In fact, it's not entirely obvious, but it turns out that if you just tried to use the free energy, you wouldn't be able to prove that right convergence implies left convergence. It doesn't. There are some counterexamples. So it's actually, in a sense, more difficult to get this global notion to imply the local notion when you have so much local stuff going on like you do in a dense graph. Okay, so we had to have we had to have it for all microcanonical free energies. So that's one difference. For right convergence for dense graphs, we had to restrict to soft core H's. We had to allow any color to be next to any other color. Okay, so when you have hard constraints, it's very difficult to color a dense graph. Okay, so here we can relax that and talk about any H. However, I talk about right convergent on H. Okay, so here I have a particular H. Let's see, do I have there. So it's for a particular H. And so a natural question is, does left convergence imply right convergence for all H as it did in the dense case? And the answer is no. There are counterexamples, which I'll give you in a couple of slides. It's actually pretty obvious that there are going to be counterexamples when you start to think about it. Okay, so other notions. There's a very natural notion that Itai and Oded came up with, I don't know, it's probably 15 years ago or something. So what they did was they took a sparse graph, they chose a site uniformly in that graph, they looked at neighborhoods of that site and looked at the induced graph on that neighborhood. Okay, so if something wandered out of that neighborhood, it didn't contribute to the induced graph on the neighborhood. And then they looked at the probability that this induced graph was isomorphic to some fixed rooted graph. That's going to add up to 1 because of the bounded degree here. And what they said is that a sequence of sparse graphs is convergent if the probability over the choice of the vertex that the ball of radius r, that the induced graph on the ball of radius r is isomorphic to some given f. If this converges for all radii and for all f's, then it's Benjamini-Schramm convergent. That's a very natural notion, okay? That's saying that locally things are converging. Notice that if GN didn't have bounded degrees, they would still talk about a sparse graph. And then I would have to put in a tightness condition like this, but here I don't have to put it in because I've got bounded degrees. Okay, so this is a very natural notion, and it turns out that this is the same notion as our notion of left convergence for these graphs, okay? So in particular then, the limit of a left convergent sequence can be described in terms of a rooted random graph. And we can think about some obvious sequences of graphs G. We can think of the d-dimensional grid. That converges. We can think of the d-dimensional torus. That converges. We can think of the d-dimensional even torus. That converges. And they all converge to the d-dimensional grid rooted at 0 in this sense, where I just look at the local neighborhoods. Okay. Also, if I look at the d-dimensional grid or at the d-dimensional even torus, a simple subadditivity argument over here tells me that these are right convergent, it turns out, okay? So for all H, okay? So this is just a really simple argument, okay? Because all I want to do is I want to show that the log of the number of homomorphisms converges, and I got subadditivity, I've got nice monotonicity, so I'm done. However, if H is bipartite and N is odd, so just think of an odd cycle getting bigger and bigger, I can't color it with a bipartite graph, right? So I'm not going to be able to color it. There are no homomorphisms. Okay, and so the log of that is equal to minus infinity, and so this is not a right convergent sequence. There are no colorings. Okay, there aren't an exponential number. There are none of them. Okay, so what this tells us is that right and left convergence are not the same for sparse graphs, and in particular, left convergence, like we have up here for this nice torus, my nice odd cycle, doesn't imply right convergence on all H, okay? If H is bipartite, it doesn't imply right convergence. So, doesn't imply right convergence on any H or on some natural class of H's. Okay, and the answer is yes, that it does. And here we really thought about it coming from a stat-mech kind of viewpoint. So, okay, let H, so this is our coloring graph, be a looped graph. So, the loop corresponds to, red sites being able to be next to red sites, blue sites being able to be next to blue sites, if that loop is in there. And what I'm going to do is I'm going to define the complement of that graph to have the same vertex set, but if something is not in the looped graph, then it's in the complement of the looped graph. And I'm going to define a parameter which is the largest degree in the complement of the graph H over the number of vertices of H. Okay? So this looks like kind of a weird parameter. But let's just think about it. If H is the completely looped, complete graph, okay, what does that mean in terms of coloring? Can you color with a completely looped, complete graph? Well, of course you can, because anything's allowed. I'm allowed to have V of H colors, and I'm allowed to put anything next to anything else, okay? So that is independent colorings, okay? And if you think statistical mechanics, that sounds a lot like high temperature. I'm allowed to do anything that I want, okay? And so what this parameter lambda is it's like an inverse temperature in statistical physics. if H is a completely looped complete graph, H complement is the empty graph. So this lambda is equal to 0, okay? And that's like beta, the inverse temperature, being 0, temperature being infinite. I'm allowed to put anything next to anything else, okay? And it turns out that we're going to look at graphs for which this lambda is sufficiently small, okay? Okay, so left convergence will turn out to be the same as right convergence on sufficiently dense looped graphs H. That is, graphs with parameter lambda of H small enough. So the first theorem is that, and this is what was failing for the bipartite graph H, and G being just an odd cycle. If Gn is left convergent, then it's right convergent on all looped graphs H with lambda of H less than 1 over twice the maximum degree in G of n. And if you know statistical mechanics, 1 over twice the degree, the inverse temperature being less than 1 over twice the degree is the kind of thing you often see in a high temperature expansion, in kind of an optimal high temperature expansion. Okay. And if Gn is right convergent for lambdas small enough, if there's some lambda such that it's right convergent for all lambdas smaller than, for H's with lambdas smaller than that, then it's left convergent. Okay. So what I'm going to do is first give you an idea of the proof, and then I'm pretty much going to take you through the proof with cheating a little bit in places, or assuming you know cluster expansions in places, and if you don't, well, Christian had some very nice notes on cluster expansions that he never completed years ago, so maybe he'll complete them and people can learn about them. Okay, so consider a normalized homomorphism number, okay? So the number of homomorphisms from G to H divided by V of H to the V of G, okay? And what I want to do is I want to look at the log of this, so I just take the log of both sides, and I divide through by V of G. And this guy here is the free energy, or the limit of that is the free energy. So it's this thing that I want to study. Okay, so what I'm going to do now is I'm going to look at the Mobius transformation of the thing that I want to study. This is what I want to study. This is my free energy, basically, or when I divide by V of G, it's my free energy, and I want to look at the Mobius transformation of this, okay? It's the kind of thing that you typically do when you're doing cluster expansions, okay? So the Mobius transformation you can just take to be defined by this. So I look at subgraphs of the graph F, and I take -1 to the size of F delete F prime, and this is the, and I multiply by the log, okay, which is the thing whose Mobius transformation I'm interested in. Okay, and
a subgraph here means deleting edges from it, right?
Deleting edges, yeah.
You keep all the vertices and look at the
Yeah. And so now I can use inclusion, exclusion to invert, and there are different ways of defining Mobius transformations where I either put, all the mess in one, or I put part of the mess in one and part of the mess in the other, okay? But if I use inclusion, exclusion, and just plug things in, I find that this is what I get, which is one of the useful properties of a Mobius transform. Okay, so now it turns out that that there are a few things that I can do with F. If F is disconnected, then U turns out to be 0. And why does U turn out to be 0? Because T, you'll remember, is basically the number of homomorphisms, okay? And so if the first argument turns out to be disconnected, then T is going to factor over it, and so U is going to turn out to be 0, okay? And also, if the first argument, so think of G up here as being just one site, okay, then I'm trying to map one site into an edge. Well, I'm not going to get anywhere, okay? And so T is going to be 1, and U is going to be 0. So I can take this now, in fact, to run over connected Fs, okay, with size at least 2. Otherwise, this vanishes. Okay. So now what I want to do, let me just go back for a second. Over here, I want to write it differently. So I want to look at all F's of a particular form, and I want to resum it looking at all F's of a particular form. So what I want to do is I want to look at the number of times that the graph F appears as a subgraph in G, okay, the number of injective homomorphisms, okay, so where I don't double my edges, okay? And so here now I can go over isomorphism classes of simple connected graphs with V of F equal to 2. Okay, so now I'm summing over isomorphism classes, which is always a nicer thing to do. I don't want to have to worry about the relabelings of this. Okay, so what is this? This is almost my free energy. If I divide by the volume of G, and take the limit as the size of G tends to infinity, this is my free energy, and what's going on this side? Okay, well, as I just said, right convergence on H is equivalent to convergence of the free energy, which is this. So that's this guy up here, okay? Now, how about left convergence? Well, by definition, left convergence is convergence of the subgraph density. Subgraph in what sense? The homomorphism density, okay, for all connected simple F's. But I can write this guy in terms of the injective homomorphisms plus more stuff, where I'm not doubling the edges, okay? And I can divide through by the size of G, and as I take the size of G to infinity, then, so I have an inclusion-exclusion where I say the number of homomorphisms is the number of injective homomorphisms plus another term minus another term, blah, 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 okay? And everything else is going to get wiped out when I divide by V of G. And so, in fact, this guy is the same as what I'm trying to look at in order to decide on the subgraph density, the question of left convergence. So now what I have is I have one equation which relates on the left what I need for right convergence for the free energies, and what I need on the right, the subgraph density. So it shouldn't surprise us so much that the subgraph densities and the subgraph densities and the free energies, that convergence of subgraph densities is the same as the convergence of the free energies, except that we know we have a counterexample. So it can't always be true, okay? But what we'd like to do is, in order to show that the subgraph densities, that convergence of the subgraph densities implies convergence of the free energies, what we need to do is we need to show that we can cut off the tails of this sum. Then, of course, we can divide through by 1 over V of G, and then that we can move the limit in. So we can only move the limit in if we can cut off the tails. And in fact, if H were a bipartite graph, we would not, and G were a sequence of odd cycles, we would not be able to cut off the tail. So it's not an entirely trivial thing to show that you can actually do this. Okay, and to show that right implies left, what I need to be able to do is invert this. So I need that after I have cut off the tails, the resulting finite matrix that I have here has high enough rank that I can invert it. Okay? So that's what I want to do, and that's what I'll do in the remaining 20 minutes or so, roughly speaking. Okay, I mean, I'll sweep some things under the rug. So proof that left convergence implies right convergence for sufficiently dense H. So this is like high temperature. This is sufficiently independent colorings, okay? Okay, so here we are, the same equation that relates convergence of the free energies to convergence of the subgraph densities. And so now somehow the fact that lambda is small, the fact that H is sufficiently independent colorings has to come into this. So I'm going to rewrite T using just a simple expansion. Okay, T is the number of homomorphisms of G into H. So this is an edge in G. This is an indicator function of the fact that the edge should be in H. Okay, that's 1 minus the indicator function that the edge should be in H complement, that the edge is not in H. Okay? And so I just write it like this, which looks like I've taken something which is pretty nice, and it looks like I've made it into a mess, actually, because I put signs in there, okay? So why have I done that? Okay, well, this guy factors over connected components of H. So actually, these are polynomials in with F running over connected subgraphs of G. So this guy here is a polynomial, okay? This guy here is a polynomial in these variables, okay? And so polynomials are nice things. So, okay, so we've got this. So how would I try to estimate this? Well, I can think of 3 ways to try to estimate it. Coming from statistical physics, Debrucian uniqueness usually gives me the best estimates. It's usually also the hardest to do. And if I did that, I would get right convergence up to 1 over 2D as stated in the theorem. Okay? If I wanted to do something a little less than that, or I didn't know about Debrucian uniqueness, I might still say, look, these Z's have all these signs. What I want to do is I want to resum somehow and put F's together so that I can take advantage of the signs and not lose too much. If I do that, I can get this bound, or I can just be really sloppy and I can say, let me just take the absolute value, let me forget about it, and just see if I can get the result for lambda sufficiently small. So that's what I'm going to do here. Okay, so here is where lambda being small comes into it. So remember, this Z is this function up here, this weird function up here. And it turns out that this is bounded by lambda, this kind of inverse temperature parameter, this, this density type parameter or low density type parameter to the number of edges in F minus 1. And okay, and so how do I get that? Okay, I mean, this is just a crude bound, as I said. If I were using Debrucian uniqueness or something, I would be a lot smarter about it. But let me just plug in what the definition is. So this is the definition. Now I'm supposed to count the number of homomorphisms. Count the number of homomorphisms from what to what? From F to H complement. So here's an edge in F. Here's an edge in H complement. Now, instead of looking at F, which I really know nothing about, let me look at a spanning tree of F, so I have no loops, okay? I'm allowed to do that because that just means I have a smaller number of edges, so it just makes the sum bigger because these factors are less than 1. Or no, it makes the sum bigger. So here, so what am I going to do? I'm going to start with a leaf of my spanning tree, and I'm going to say, how many things can I map this to? Well, I'm trying to go into H complement. And so I can't map it into more than the maximum degree of H complement things, okay? And now I just work in, okay? So now I just come in from the leaf, and I do it again, and I do it again, and each time I can get D of H complement at most, and I come in and I have VF minus 1 leaves, and now I've got one site left, and what do I do with it? Well, I can just bound that by V of H complement, which is the same as V of H. Okay, and I plug all that in with these factors that are in the definition of Z, and I get this bound. So this is a really, really crude bound. I mean, I've thrown away all this structure on F. I haven't combined different Fs. I'm not being very careful. I'm not smart like, you know, Schlossman and DeBruschen. I'm just doing this crude thing with the spanning tree. Okay, so now back to the proof. So we wrote this T of G as a polynomial in these variables. I got this lemma by doing this really crude thing with spanning trees. So now I'm going to do what kind of a classical mathematical physicist would do. I'm going to do a multinomial expansion of this, or some combinatorialist would do this also. I'm going to do a multinomial expansion of this about 1, okay, which is an expansion of log t about 0. So here it is. I mean, this is just this expansion of, you know, in these variables. I said it's a polynomial, so here's my multinomial. Okay, now I'm going to look at the uniquely defined U, which comes from the Mobius transformation of that. Okay, if I've got this, then, you know, then this guy is itself going to be a convergent series in these variables. And if I go through, and because these had to add up to G, turns out that this F has to be a union of these FIs. If I just go through and use my bounds on Z, it turns out that I get an upper bound on U. If I'm more careful than that, and I have some additional properties of the graph H, then, then in fact, I can get more than that, okay? Then I can get, over here, I can get that it's order of, that it's Z times 1 plus O of lambda, which I will use later even though I didn't show it to you, and it's only true if H has some extra properties. Yeah? Did I use that? I mean, H could be looped, but it need not be looped. Right, H is all possibly looped things, but it doesn't have to be looped. And in fact, I mean, when H is a completely looped graph, then H complement has no loops whatsoever. Okay, so now I've got this, and that's my tail. Okay, and this just shows that I have exponentially decaying tails. So I can divide by 1 over v. I can move that in. I can move the limit inside. And so then I get that if it's left convergent, because I can move the limit inside, then I'm going to get that this converges also. So I'm in good shape. So to prove that right convergence implies left convergence, we need to invert this relationship. Okay? So, and as I said, I'm sweeping a few things under the rug, but they just make things uglier in certain ways, but it's not really important. Okay, so now what I want to assume is that for all H's, for all models, colorings which are like high temperature, which are pretty free, if it's right convergent for all of those, then also the subgraph frequencies converge. So here we are, the same old equation again. And so I want to be able to invert this relationship, as I just said, for H dense enough. Okay, so now what I'm going to do is I'm going to say, let me look at all graphs F that have no more than M sites in them. Okay, so I have capital M of those. And if H is dense enough, then by the proof that we just went through, we know that sum had small tails. We know this thing that I told you that we almost got. And So here, this is from the fact that the sum has small tails. Here, I actually didn't quite prove this for you, and I'm in fact cheating because it requires that H has some extra properties, and the H's I choose will have those properties. And then I just use the definition of Z. Z is -1 to the E of F times T of F and H complement, and here's T of F and H complement. Okay, so I want to be able to invert this. So how do I invert it? Well, I've got a matrix on this side. I've got to pick some H's. Let me try to pick M H's and hope that this matrix with the M H's that I choose is high enough rank that I can invert it. So can I find some graphs that are the graphs that define the models that I'm looking at, which would allow me to invert this? Okay, so that's what I just said. This has to be invertible, so I have to find M dense H's such that this matrix here that's left in this finite sum is invertible. Okay, well, so I look at this. I know almost nothing about this. So I say, well, what do I know is invertible? Well, it turns out that if the FIs are the set of all connected graphs, turns out it's important of size at least 2, up to some finite size, then the number of homomorphisms of Fi into Fj is invertible. That is a high enough rank matrix, okay? So maybe I should choose these to be the Fj's, because I don't know very much. Okay, so that's what I would like to do. I'd like to choose those to be the Fj's.
So is this lemma hard?
This lemma, if I write out the home, I can write the home out as injective over surjective with some other factor in there, and the injective is for all graphs up to a certain size is an upper triangular matrix, and the surjective is a lower triangular matrix. So so it's not hard. It's not a hard lemma. So, okay, these are just, I didn't know it before we did this, of course, but it's not a hard lemma. Right, it's a product of an upper triangular matrix, a lower triangular matrix, and a diagonal matrix, which is the automorphisms. So, okay. However, there's a big problem, which is that this was only true if H was dense, and now I want to take H to be the complement of F, and F is a list of all graphs of size at most m. So those are not, so, the complement of all graphs of size at least m is, some of those are not dense graphs, and, some of the F's are not sparse graphs, right? So I can't do that. So now I'm going to do a trick, which is I'm going to take a sparsified version of these graphs. These F's are just all graphs up to a certain size, and I'm going to sparsify them. So what I'm going to do is I'm going to take a large number of singletons, very large number of singletons, Q of them. I'm not going to roll Q minus the size of F of them. And I'm going to take the union of those with F. So I'm going to take F, which is the graph that I've got. I want F to be sparse, okay? And it may be sparse and it may not be sparse. If I add a ton of singletons to it, then it's sparse, okay? So that's what I'm going to do. I'm going to add a ton of singletons to it. And I'm going to call that, so this guy with this many singletons in it is sparse if I take enough singletons, okay? And then there's this really nice thing about homomorphisms. Homomorphisms behave very nicely on disconnected graphs. They just kind of ignore them, okay? So I can add all this stuff to it, make it sparse, and it's just going to ignore it, okay? So the homomorphisms, so I defined HJ complement to be this, and it just goes right through. And it just doesn't even see the thing that I used to make that sparse. Okay, and now I'm done. Now I'm able to now I found these H's, which allow me to invert this. I've got these approximate equations. They were approximate because it was plus something small for Q, for H dense enough. And I certainly can take H dense enough by taking H complement to have enough singletons in it. And so I've got this. I can invert this. When I invert this guy, then I get N on this side, and I get the stuff that has to do with the left convergence on this side. I invert it. I get the stuff that has to do with the right convergence on that side. M was arbitrary. So now right convergence implies left convergence. Okay? So what we found is, whereas in the dense case, there was the same amount of information in knowing all my subgraph densities, okay, and knowing my edge density, my triangle density, my Peterson graph density, blah, 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 and knowing all free energies of soft core models on that graph, okay? In the sparse case, this is not true anymore, but it is true that knowing all the free energies for sufficiently independent models, for models which have a relatively small number of constraints relative to the maximum degree of my sparse graph, that contains the same amount of information. Okay, it was just too much to ask that, left convergence at subgraph frequencies imply this for all H's, but it is true that I get a right and left convergence equivalence when I say I'm only doing this on sufficiently high temperature models on the graph, where the definition of what is high temperature has to do with the maximum degree of the sparse graph. Okay, so we define left and right convergence by strict analogy, really, to what we did in the dense case. We get this result. It's still, though, we found somewhat disturbing that that we had this definition that didn't imply right convergence. So, here, okay, as I said, the density of H is inversely related to the uniform upper bound on the number of neighbors of the sites in G, analogously to high temperature. But left convergence, as I showed you with the bipartite graph and the odd cycle, does not imply right convergence on all H. So the question is there a stronger notion of convergence, okay? Stronger than just asking for all the subgraph frequencies, but not hopefully ridiculously strong, which will imply right convergence for graphs of bounded degree. And that, in fact, is what Christian is going to talk about in half an hour or so. Okay. That's it. Look at yeah, which is letting it be not so. I mean, yes, it's a way of making it sufficient. Yeah. Mm-hmm. But it will again be related to the maximum degree or the upper bound on the degree of the G's.